Constant acceleration. Constant acceleration is a special case. It has three formulas you are quite familiar in high school. First is v equal to v0 plus at. The velocity at time t equal to velocity at time 0, initial velocity, plus the constant acceleration times t. Second equation is the distance traveled, x minus x0, okay? This is equal to v0t plus half a t squared. This formula you should be familiar with. And we have a final v squared minus v0 squared equal to as, and s equal to x minus z. Okay? These three equations we are going to use again and again. You should remember that. You have five quantities: v, v-ling, a, t, and s. Okay, we have three equations. So in order we can find the answer, we have to know two. Okay, out of these five, you have to know. Now, special case. Okay, a is constant. Okay, a can be larger than 0 or smaller than 0. dv. Move this one. A dt. We do the integration. And we find v, this integration, differentiation, cancel out. V equal to integration a dt. And in this special case, a is a constant. So it said, let me out. Okay, I'm constant. And then integration, integration is t. So get at. Okay, vt. V equal to at plus constant. This constant, okay, is the initial condition. Okay. When t equal to 0, v equal to v0. This is called the initial velocity. When t equal to 0, v equal to v0. So we find, okay, c1 equal to v0, and we put it inside. Okay, we got at plus v, and rearranging v0 plus at. We're familiar with that one. Okay. Or we can do a different way. It is a dv equal to a dt. We do the integration. T equal to t0. This is v0. T equal to t. V is v. And we do this one. This one is v minus v0. This one is at plus c. At, no c, sorry, is this definite integration. Okay. So this is actually this one. We learned that velocity vt is dx dt, the derivative of its position with respect to time t. Now we do this one, then dx equal to v dt. And we do the integration. Okay, this is x, right? Integration, differentiation x. This vt, we do that. Vt equal to v0 plus at. And we do the integration. This is a v0t. This is half at squared plus constant. It's very simple integration. Okay. And c2 is from initial condition. When time equal to 0, the position is x0. Okay, initial position. So we put it inside, we get x0 equal to v0t half a 0 squared plus c2. We get c2 equal to x0. And we put it inside, okay, we get s equal to x minus x0, the displacement, equal to v0t plus half alpha t squared, which you are quite familiar with. Or we can do it a different way. We just do the integration. Okay? dx equal to v dt equal to v d t. We do the integration. Okay? A definite inversion. Okay? T equal to 0, v, x equal to x0. T equal to any time t, x equal to any time t, x. this integration is x minus x0. This equation equal to v0t plus half t squared. This is exactly at this one. Okay, at this one. Look at the curve. This is acceleration to t. A is constant, a special case, constant acceleration. So this is a line. And we move this v equal to v0 plus at. This is a vt. This is a t. So this is linear. Okay. T equal to 0. This is v0. There's a tangent. There's tangent. Okay. So, okay. A. And finally, the x. Okay. This is x0. This is a x a function of t squared. So there's a parabola. Parabola. This is the curve. Okay.
A ball rolling down a long incline will be used to show how position, velocity, and acceleration of the ball change as it moves down the incline. 5 lights arranged along the length of the track flash simultaneously once per second. As the ball rolls down, it is directly above each of the lights just as they flash. This gives us a record of the positions of the ball at 1 second intervals. This is how far the ball traveled in the first second. This is how far the ball traveled in the first 2 seconds, 3 seconds, 4 seconds. We will move this distance up to a graph to keep track of position versus time. Does position change linearly over time? Next, we will graph the average velocity of the ball during 5 different intervals to see how velocity varies as the ball rolls down the incline. The ball moved this far during the first second. It moved this far during the next second. This far during the third second. The fourth second. This gives us a graph of the velocity of the ball over time. Does velocity increase linearly? Now we will graph the changes in velocity versus time by graphing the differences in successive velocities. What does this tell us about the acceleration of the ball? The acceleration is constant. We will use a nearly frictionless air track with the glider floating on an air cushion to demonstrate accelerated motion. When the track is level, a push is required to move the glider. It then moves at a constant velocity as shown by these dots that track the position of the glider at half-second intervals. When we tilt the track by placing a 1 centimeter high shim under one end, the glider moves down the track. What can we say about the magnitude of the velocity in this case? The glider's velocity increases with time. It accelerates. If we increase the tilt of the track by doubling the height of the shim, the acceleration increases. When the shim height is increased to 3 centimeters, the acceleration increases again. This split-screen view shows the glider accelerating at all 3 angles of tilt.
V squared equal to V0 plus AT squared. We get this one is V0 squared plus 2V0 AT plus A squared T squared. Okay, and look at this one. Okay, we take the 2A out. It's a V0T plus half AT. What is this one? This is displacement x minus x0. This formula, okay, so we write this v squared minus v0 squared equal to 2as, s equal to x minus a. This is the third formula for constant acceleration. you have to remember. Another look at constant acceleration. S equal to x minus x0 displacement, v0t plus half at. We rewrite it in two terms. One is v0t, another is half at. We can look at it, okay, as two movements. One is v0t plus half 0 at. One is 0t plus half at. What does this mean? This is the movement with acceleration 0, uniform speed v0. This is initial speed equal to 0 and constant acceleration. So this is a uniform movement with the initial velocity v0. And this is the constant acceleration with v0 equal to 0. So a constant acceleration movement can be looked at as a composite of two. The direction of the acceleration of a point depends not only the change of its velocity, but also on how the reference axis is chosen. Okay? For example, this is acceleration actually. If we take the reference frame in this direction to right, and then this A is larger than 0. Same acceleration. If we take the reference frame x positive to the left, in this case, A is smaller than 0. Whatever, they are the same movement. Okay? Depends on how you choose the direction of frame. Both are right. Both are right. The magnitude of the acceleration of a point depends on the change rate of its velocity. It has nothing to do with magnitude of the velocity itself. Look at this one. We have familiar this vibration, okay? And you look at this one. At this neutral point, it goes back velocity to the last. X is very small, velocity large. And at the two extreme points, okay, velocity is 0, but acceleration is very large. So position, velocity, and acceleration are independent with each other. Their dimensions are different. So big velocity does not mean big acceleration. Acceleration is the change rate of velocity. Look at this is the velocity. At x smaller, velocity can be larger. X larger, velocity can be smaller. That's different things.